the energy stored in the configuration, isn't it? So that is written like this, isn't it? Integral of E square d2. Again, I am not discussing that inconsistency because he also hasn't answered that one here, okay? So he is postponing that one into 11th chapter. So integral epsilon naught by 2 E square d2. The total is energy. Okay, so now you can call this one as energy density. You have to integrate this one entire space, okay, all space. Now this is energy per unit volume into volume integrated. You got total energy. Is that okay? So that's why we call this one as epsilon naught by 2 into E square. We call this one as energy density. Is that okay? That's the one aspect. Is that okay? Yeah. So next one is the superposition principle. Energy will not follow superposition principle. Is that okay? They may design question. Electric field will follow superposition principle. Force will follow superposition principle. Then electric field, then potential. But energy is not. Look at here. Why energy proportional to E square? If E follows superposition principle, energy should not, isn't it? Now look at here. Suppose this electric field is a result of E1 plus E2. Is that okay? And this electric field will produce, suppose W1 as the energy. Suppose this electric field will produce W2 as the energy. Suppose this produces W. Now how they are related? Not W is not equal to W1 plus W2. W you have to write it as again epsilon naught by 2 integral E1 plus E2 whole square d2. E square d2, that means E1 plus E2, isn't it? Vector whole square, again magnitude, okay? So what do you mean by vector whole square? Dot product with itself. When you make dot product with itself, what would happen? E1 square plus E2 square plus 2 E1 dot E2. Am I right? So d2, that's why I can write epsilon naught by 2 E1 square d2 plus epsilon naught by 2 E2 square d2. You can call it as W1. You can call this one as W2. Is that okay? So plus, so 2 epsilon naught by 2, am I right? Integral E1 dot E2 d2, isn't it? So that's equal to W1 plus W2 plus some extra term, that is the last term, this term. Okay, so that's why your energy will not follow superposition principle. Is that okay? Energy, you can't just like calculate energy due to one part of the charge configuration, energy due to other part, and you can't add them. There is one more term here. Okay, so now try to apply this one, this last formula. W is equal to W1 plus W2 plus epsilon naught integral E1 dot E2 d2. E1 is electric field due to one charge configuration. E2 is electric field due to other charge configuration. Electric field superposition says this one, am I right? But energy stored, it is not following the same equation, similar equation. Okay. Now try to apply this one in problem number 37, 2.37. Okay. He has taken concentric shells. Okay, he has taken concentric shells with inner shell Yeah, we better to request him, isn't it? Daily he will announce at this time only. Suppose plus q minus q, whatever, okay? So plus q means plus q is uniformly distributed over the spherical shell, okay? Minus q is uniformly distributed over the spherical shell. I think you might have applied Gauss law. So there exists only electric field in this region. Outside it is 0, inside it is 0, because Gaussian surface will not have any what you call charges, isn't it? Now that is one thing. One way is, so find the net electric field and just follow this one. Am I right? So I mean just E square d2. Okay, that's the one idea. Other idea is, so assume that only inner shell exists. Find the energy due to that one. Okay, assumes that only outer shell exists. Find the energy due to that one. And find the electric field due to inner one, only inner one. Find the electric field due to only outer one. And just use this one. Try to verify this one. Look at that formula. For this particular question, 2.37 or 37 question. 36 question is this one. I mean, find the energy. But if he asks only energy, don't make it lengthy. Okay. Just find resultant electric field. Resultant electric field exists only in this region. Am I right? Resultant electric field exists only in this region. So, and just integrate from suppose this is A, this is B. So, just volume integrate so that your radial distance from A to B. Okay, E square D2. That's the best way. So, again, try to verify this formula also. So, shall I move on? Yeah. E1.E2. Yeah, definitely. Definitely. So, now I haven't edited anything. So remember, E1 plus E2 dot E1 plus E2. Dot product with itself, the square of the vector, isn't it? E1 dot E1, E2 dot E2, E1 dot E2, E2 dot E1. Dot product is commutative. That's how 2 E1 dot E2 came. That's most general. So, but in this case, I think you will get 180 degree. Am I right? E1 dot E2. What is the angle between them? In this case, you haven't solved this one, isn't it? Because this will produce electric field outward. This will produce electric field inward. Outside the region, you will get E1 radially outward, E2 radially inward, like that it will come, okay? Just check it out, okay? Yeah, so try to verify that one. Yeah, is that okay? E1 dot E2, okay? I'm not writing theta. So now, let me slowly get into next concept, conductors. Whenever I hear, so whenever that word comes into mind, so my hand will go into my pocket. I will search for change. Is that okay? It's very scary thing. Whenever I take bus, I'll get scared because of whether I have change or not, isn't it? Sometimes what they will do is they will give 100 rupees. So they will so tell us to give 50 rupees to other one, isn't it? If they want to give 50. Yeah. Okay. So bad conductor, am I right? No. Just forget that. Okay. Yeah, why he introduced that part separately, isn't it? So until now, whatever he discussed, charge distribution, he hasn't mentioned whether it is conductor or insulator. He just said there is a charge like this, charge configuration like this, and apply your Gauss law, whatever. Okay. So now we have to think of, some property of conductor. Okay. So how do you define a conductor? Perfect conductor, suppose. Resistance is 0. Wait a second, still we haven't defined current here. Yeah, so write down one sentence. A perfect conductor contains unlimited supply of free charges. A perfect conductor contains unlimited supply of free charges. A perfect conductor contains unlimited supply of free charges. That's how we can define. Yeah, so there are no perfect conductors. Obviously, you know, it's not unlimited, it's finite. Am I right? So again, what is the most perfect conductor? I mean, what is the what do you call? What is in the top? Silver or gold? I think silver. He mentioned later, okay, in the electrodynamics chapter. I think silver, okay. Silver is the most conducting one. Yeah, we shall see that one later, okay. Now, properties of conductor. Properties. Conductors. What are the properties? Will not give change, isn't it? Yeah. So not like that. So basic properties. Basic properties. First one. Now look at here. You have to use all of your formalism, whatever we have done until now, to prove these properties. Is that okay? Now again, it's not just like what we have stated in our class 12. We had not much mathematical background. Is that okay? Now you have to give mathematical explanation for each and everything. Okay. So now first one is electric field equal to 0 inside a conductor. Inside a conductor. How do you prove that one? Again, I think he also have given this one in a argumental way. Yeah, first try argument. How do you argue that electric field inside a conductor is 0? Always remember, whatever the situation. Yeah, then charges can move, isn't it? Freely move. Free charges means charges can freely move. Yeah, they will respond. Am I right? So now, look at here. I have a slab, metal slab. Is that okay? So perfect conductor. I am going to place that one in an external electric field E0. Is that okay? I am going to place that one in external electric field E0. Is that okay? If I place that one in external electric field E0, now electrons will be dragged one side. Electrons, I think it will drag opposite to the electric field. Am I right? Electrons will experience force opposite to the electric field because of negative charge. Am I right? Q into E is the force, isn't it? So now electrons will be dragged here. That's why negative charges will be accumulated here. Am I right? So or I should not write it outside. I have to write like this to be in the safer side, isn't it? So now actually only electrons are free charge carriers. Okay. So then what would happen here? Nucleus, which are atoms which lost electrons, so they will remain here. Okay, we call them as ions, isn't it? That's how it happens. But in the point of view of electrostatic, we don't have to worry about electron or ions. Okay, we just have to now. So charges will move freely. That's it. Is that okay? So now positive ions will remain here in the actual sense. Electron will move like this. Now the question is, how long they will move? Isn't it? They will move until they cancel out its effect inside. Is that okay? Inside, so they will produce electric field, its own electric field. Let me call this one as EI. Is that okay? Let me call that one as EI. So I mean this electric field and this electric field will cancel out with each other inside. Is that okay? So electrons, free charge carrier, they will move until it cancel out external electric field inside. External, when you place that metal in or when you place that conductor in external electric field, so external electric field will try to induce some electric field inside, isn't it? Now charges will respond in such a way that we can't communicate with them. But there was one movie, Telugu movie, where he communicates with the Indian Railway and he makes the entire platform empty, isn't it? Have you seen? Yeah. Yeah. Okay. Now look at here. Okay, it's not again any question here. Yeah, whatever, what are the? No, outside electric field exists. Yeah, the inside electric field will cancel. Look at here. This external electric field. Now I have to write like this. Inside electric field is 0. It is like that. I mean, EI plus E naught equal to 0. It will happen inside. Or whatever the electric field, so that is due to this what we call induced charge, induced charges. So that is exactly opposite to external electric field. That's why inside electric field is 0. You can write this equation inside. Is that okay? Outside, this field only exists inside. Okay, this field only exists inside. So now look at here again. You can say, I mean, inside you can write this equation inside that one, and inside whatever the electric field that is created due to those charges. So that's exactly equal and opposite to the outside electric field. That's how it is get cancelled. Okay. So, but it's also not comfortable, not mathematical. Am I right? So argumental again. Charges will move in such a way that charges will move until they cancel out the external electric field inside. Isn't it? That's the argument. So now can you just write? So better write that one. Induced charges produce their field which is opposite, which is equal in magnitude, and opposite in direction to the external field. Yeah, wait a second. Let me use Gauss law. Wait a second. Yeah, what is the sentence? Induced charges will produce electric field inside, which is equal in magnitude, opposite in direction to the external applied electric field. Okay, so that's the best sentence. And the whole process is instantaneous. That's very important. Is that okay? Charges will not take much time to move around. Okay. So they will take some time. Okay, for a perfect conductor, they will not take much time. Instantaneous. It will happen very instantaneously. We shall discuss this time parameter again in the electromagnetic waves chapter. Okay, that also does matter. So we don't have perfect conductor. Am I right? We don't have ideal conductor in nature. It will have some resistivity. Is that okay? It will have some resistivity. Charges will take, in actual sense, finite time to travel, but right now we shall take an ideal conductor where the whole process is instantaneous. As soon as you keep it in the external electric field, as soon as you keep that conductor in the external electric field, so charges will be induced so that the electric field inside is 0. So second one is, again after this argument I can show this one. Okay, after this argument. So rho is equal to 0, volume charge density is equal to 0 always inside a conductor. Why? Again, don't use this one now. Argue independent. Once you argue independently, you can use this one to find this one. Curl equal to 0 already. Is that okay? Like that. Divergence will also be 0. Yeah. How do you argue? Yeah, okay. Electric field exists. If there are charges inside, then electric field exists. No, don't use electric field concept. If there exists charge density, I mean that should be the density should be because of free charge carriers, conductor, isn't it? So if there are free charges inside a conductor, I mean suppose positive or negative. Suppose if I take positive, they will repel with each other, isn't it? So how long they will repel? They will repel in such a way that so charges will move out to the what you call surface. Is that okay? So that no volume charge exists. Are you getting my point? The next sentence is there will be no volume charge density. So if you try to give any charge to the conductor, they will always reside on the surface. Why they will not reside inside? Because of the repulsion. Because of the repulsion, so that volume charge density will not exist usually. Is that okay? Even though if it exists, within no time, those volume charge, they will move out to the surface. Is that okay? That is the only place left. Is that okay? Can you write one sentence quickly? Why can't? Yeah, definitely. They will repel with each other even in surface, but that is the only place left. No, inside the volume they are free to, it's a kind of how to argue. I'm not finding any analogy. Have any analogy? Inside it is free to move, but it can't move outside the surface. Inside, yeah, look at here. If I have free charges in a space, not a conductor, okay? Suppose Q1, Q2, Q3 like that, okay? All are positive. So we are holding that one. If you leave this one, what they will do? They will move out to infinity, isn't it? Suppose now charges inside the conductor will feel the same thing. So they will try to move out, but they can't go outside the surface. Again, we have to think about our work function. So to take off the electron from the surface. Is that okay? So they will not go outside the conductor. They will not escape from the surface. So they can only move out to the surface. That's how they fail, isn't it? Because when we just leave these positive charges, they will move out to infinity. Just like that it will happen, but they can't go to infinity. They have to go to the surface. Yeah.
When they come to the surface.
Yeah, definitely. That is the only place.
When they come to the surface. So inside volume there is no charge.
Okay, so let me give some positive charges here. Now remember, if you try to induce some charges inside, so the process started from this one. Okay, they move out to the surface. This is the equilibrium condition. Now they will not be disturbed. Is that okay? This is the equilibrium condition. Let me argue in another way. This is the minimum energy condition. Is that okay? This is the minimum energy condition. This is the minimum electrostatic energy condition. Is that okay? I mean, if suppose process will not start with this one. If you try to induce some volume charge, so they will move out to the surface. So that's how process will happen. But that is actually instantaneous for ideal conductor. Is that okay? Once they move out to the surface, they will not again come back. Remember, that is the least energy condition. Let me show that one. Is that okay? Yeah. So now, so if you try to again, the argument is, I think he hasn't mentioned, because of, so write down, because of mutual repulsion, yeah, look at here, this is the convincing, this sentence is convincing. Because of mutual repulsion, the charges naturally spreads out as much as possible, isn't it? Because of mutual repulsion, charges will spreads out as much as possible. That's why volume charge density doesn't exist. Yeah. Speak out.
Why the surface itself is the least energy condition?
Yeah, let me show that one. I mean, we shall take that one. We shall take that our earlier answer. So wait 1 second. Just take the sentence. Because of that mutual repulsion, charges naturally spreads out as much as possible. And only place is a surface, isn't it? So that's why they will move out to the surface. Volume charge density equal to 0 always. Yeah, what's that one? Again, it's nature. Okay, it's very difficult. It is becoming philosophical now. Is that okay? Why least energy? Why it will try to go to least energy? Isn't it? Again, wait a second. Now, do you remember we have calculated electrostatic energy due to total charge, which is uniformly distributed within the region of the sphere of radius capital R. Do you remember what is this one? 1 by 8 pi epsilon naught q square by R. No, 6 by 5 multiplied. So for a spherical shell of same what you call geometry, same radius, spherical shell, now charges are distributed over the surface of the spherical shell. Then its electrostatic energy 1 by 8 phi epsilon naught q square by R. That is multiplied by 6 by 5 as I remember, or 5 by 6, 6 by 5. Is that okay? Now look at here, this is little higher than this one, isn't it? So that's why if you give some freedom, definitely it will try to attain this one. Or if you give charge q, so it will go to the surface. I mean, so free charges inside the conductor will have this one. Will try to have this configuration, but they can't move. They can't go outside the conductor. So that's why it will try to attain this one. This is the minimum energy, minimum electrostatic energy. Is that okay? Again, it will try to attain minimum electrostatic energy. That is another argument. Is that okay? Pure mathematical argument. So repulsion, and they will try to be as far away. So that is the best argument, best what do you call argument. Is that okay? Without mathematics. So now rho equal to 0 inside a conductor. Again, if you try to give any charges, they will move out to the surface within no time for an ideal conductor. They will take some time to move out to the surface for a non-ideal conductor. Okay, that's again we shall discuss in the last chapter. Okay, yeah, what's the question?
Why is there a equilibrium condition? Is there something to do with entropy?
I don't know how to define entropy here. Maybe. No. Least energy. I mean, all of our system will try to get into least energy usually. Is that okay? So it's very difficult to argue why, isn't it? Least energy is a kind of stable one. That's correct, isn't it? So to get into least energy, it will lose energy. It will lose energy. It will go to that stable state, isn't it? That is the stable state. Its energy cannot be lesser than that one. So to have higher energy, we have to supply energy, isn't it? Suppose if you want to move the charges, you have to supply energy to move them into interior, isn't it? Yeah. So that is the best argument. Is that okay?
Charges try to remain apart at maximum distance from each other. Then why it does not happen that some remain on the surface and some interior? So also they can manage distance between them.
I'm not getting. No, I explain in your way.
Charges will decide on the surface.
Yes.
They will maintain minimum distance also in surface. Some charges stay inside and maintain.
No, they are free, isn't it?
No, yes.
They will move as long as they can, isn't it? Whenever there is a.
So at the surface there will be again repulsion. So some of the charges again come.
No, I mean it has started from this one.
Why can't they distribute like homogeneous?
No, I mean the thing has started with this one. You are trying to induce some volume charge density. Is that okay? The process has started with this.
They have unlimited supply of charges.
Yeah.
So they will start to repel in the photo surface. Again on the surface they will again repel.
No, I mean that is the minimum situation. Again,
Why can't they homogeneously distribute inside so that the line is
again, suppose if they homogeneously distribute, then they will repel with each other, isn't it?
so minimum they will keep.
Now that is not electrostatic condition now. I mean, electrostatically they can't be homogeneously distributed, because again repulsion always exists, isn't it? Now they are free charges, again repulsion exists.
Even in the surface itself we have repulsion.
No, you have repulsion, so the process has started with this one. Suppose if you have taken out, so I mean you are saying uniform charge distribution, am I right? Suppose you are taken out electron from this, so from everywhere inside a spherical conductor. Is that okay? Then at that instant you got what you call uniform distribution, am I right? Now quickly they will move out to the surface because of the repulsion again. the charges again. So if it is uniformly distributed, remember, so then the question comes, yeah, they are free charge carriers, still how they are in space, isn't it? They will repel with each other and they are free to move within the conductor.
They will repel each other.
Yeah.
Such that repulsion due to one charge is opposed by same magnitude but in different direction of the so that they can attain.
I mean somewhere here,
The adjacent to
these two will cancel out each other. Now actually, so that will be charge, free charge, which is kept at rest. That's what you are saying, isn't it? Yeah, I better to take again pure some mathematical situation. Is that okay? I better to take still mathematical way. Because you can't keep the charge at rest, free charge at rest using only electrostatic force. That comes in next chapter. Is that okay? They will escape in some way. Is that okay? We shall argue that one in the next chapter. So that's because of the fact that I mean again because of Laplace equation. Let me just try to explain that one. Okay. So again, so one more thing that I have to argue here is, again, if I start with this one, then del dot E equal to 0. That's why rho equal to 0. That's how he argued actually. But I wanted to argue this one using this one. Is that okay? What did he argue is, if once you argued electric field inside is 0, but that was very argumental, am I right? I mean, it cancel out its effect like that. So now, once you argue this is 0, now del dot E is equal to 0. According to Gauss law, no volume charge exists. Okay, that also you can do, but I am trying to argue this one independently so that I can argue this one in the next step. Is that okay? Or you can go for some other curl. We haven't used curl here, isn't it? We can go for that one also. We shall see that one. Okay. Yeah. So charge again the basic property here is charges will try to be apart. I mean free charges, they will try to be apart because they are free to move inside. So that's why they will avoid this kind of distribution. They will move out to the surface. Okay, that is the best argument. So next one, any net charge reside on the surface. Third property, rho equal to 0. There will be no charges very well within the conductor. Third property, any charge, if there exists any charge, any net charge, you better write like that. Any net charge resides on the surface. Why? That is the only place. They can't go outside, but they want to be as far as away. Is that okay? That's why they will be on the surface. So next one, a conductor is equipotential. Fourth one. A conductor is equipotential. Now how do you show this one? So how do you relate that one to potential? Rho equal to 0, you can say del square V equal to 0. Not V equal to same, isn't it? Okay, surface charge density. How do you say potential is same at all point on or inside the conductor? Electric field is 0. Then you can say gradient equal to 0. Yeah. Gradient equal to 0 means potential is uniform. That's a good idea. Either okay, electric field equal to 0. No, gradient is 0 always. No. Suppose if I take, no, gradient will be 0. I mean gradient is 0 only for constant one. Yeah, obviously. Only for constant scalar, gradient is 0, isn't it? Otherwise, you will get gradient. Am I right? Yeah, definitely. Yeah, that's a good argument. Okay. So that means gradient is equal to 0. Is okay? That means V equal to constant. That's a good argument. So another argument is take any arbitrary conductor If there is any charge exists, they will reside on the surface. Okay, if there is any charge exists, they will reside on the surface. Inside electric field is 0. Now take any 2 points inside the conductor, A and B. So take this line into what is VB minus VA minus A to B, I to B or B to A? A to B, E bar dot DL bar. Now you can say one thing, why can't I move my path integral outside where there exists electric field, isn't it? If there are charges on the surface, there may be electric field outside the conductor, okay? But, so that line integral is independent of the path taken. So now what I do here is I am going to restrict my path inside. And inside, throughout this path, your electric field is 0. Is that okay? So whatever the 2 points you take inside the conductor, you can run your path integral, this path integral in such a way that your path is very well within the conductor. And inside the conductor, your electric field is 0. That's why this path integral is 0. That's why VB equal to VA. Yeah, speak out. Is that okay? Suppose you have taken 1 point here, 1 point here, on them, on that one. Okay? So, I mean, even though there exists charge, they will reside on the surface, okay? So, as much as what you call on the surface, okay? Is that okay? So, now look at here. Suppose this is point A, this is point B. 2 points on the conductor. Now, let me take 2 points on the conductor. Now, what I do here is this line integral is independent of the path. What I do here is I am going to run my path integral like this. So that again, this will be 0. So that any 2 points on the conductor is also equipotential. Any 2 points within the conductor is also equipotential. We can show like that. Is that okay? So again, whenever there is a surface charge, electric field will have discontinuity. We have seen, isn't it, in the last class. Whenever there is a surface charge, so E perpendicular above minus E perpendicular below is equal to sigma by epsilon. Is that okay? Electric field just below that will be 0. Okay. So from on the surface, I will just take my path integral so that it runs inside the conductor, so that I can show that line integral is equal to 0. Any point on the conductor is also equipotential. You can show mathematically. Is that okay? So try to do it yourself. Yeah, any question? So that's why we can write VA is equal to VB for any arbitrary points A and B on or inside the conductor. For any 2 arbitrary points on or inside the conductor. Yeah, again, try to go through your boundary condition again, okay? I mean, no need to prove that one, but keep on visiting that one, boundary conditions, okay? Perpendicular component suffers discontinuity. Parallel component suffers continuity. Am I right? Now look at here. So let me argue in this one in a different way. Electric field is perpendicular to the surface just outside the conductor. If electric field exists outside the conductor, it will be always perpendicular to the surface. Can you write other property? Remember, so write down electric field E vector is perpendicular to the surface, perpendicular to the just outside the conductor. How? How do you show? Yeah. Yeah. Wait a second. Suppose I have this kind of situation. Suppose I have very many charges here, isn't it? I have very small amount of charges here. Is that okay? So that somewhere here at this point or just outside, you may have electric field in some other direction. Am I right? I mean, electric field at any point is due to all charges around this one. Then, which moves? Charges. Yeah, that's a good idea. Yeah. So suppose let me take a part of conductor. Let me take a part of conductor. Suppose electric field is like this. So there are charges. Okay, there are charges. Suppose electric field is like this. Okay? Then there exists a parallel component. Am I right? Isn't it? Then there exists parallel component of the electric field which will try to move the charges again. Isn't it? Again, how long it will move? It will move as long as so it will move until that parallel component cancel out. Is that okay? If electric field is not perpendicular, then there exists parallel component of the electric field. So to the conductor surface. So take a small patch like this. To the conductor surface, there exists parallel component of the electric field. That parallel component of the electric field again will try to move the free charges. Isn't it? Yeah, it will move free charges. It will move free charges until it cancel out its effect. Is that okay? How long it will move? It will move until so that parallel component cancel out. If parallel component cancel out, then only perpendicular component exists. And it will happen very instantaneously again. Is that okay? Now let me start with the situation where electric field. So you try to disturb that one, suppose, so that there exists some electric field other than perpendicular direction. Then when you leave the distribution, quickly it will rearrange, or that parallel component, it will try to move the charges quickly so that electric only perpendicular component exists. So that's the argumental. Is that okay? If electric field is not perpendicular, then parallel component exists. That parallel component will tend to move the charges. Again, charges will move until they cancel out their parallel component. Okay? So what is the other one? What is the other idea? Pure mathematical. I talked about boundary condition, isn't it?
For a charge, there exists actually no
Yeah, definitely. No, I mean, you can't, I mean, you are not having only one charge over there. So, I mean, electric field is due to effect of all other charges.
If I consider it two charges.
Yeah.
So, but we have done two charges in a particular situation. So, whatever sign component, this parallel component get cancelled. Only both components.
Only perpendicular component exists.
So, for any point I choose, only perpendicular component exists.
No, that is for uniform surface. You are arguing for uniform surface, isn't it? Sometimes surface may be non-uniform. Is that okay? So somewhere it is sharp and somewhere it is very, what do you call, like this. Is that okay? Somewhere it is sharp. So then you can't argue like that, isn't it? I mean, you are arguing for a kind of very symmetric problem, isn't it? Now again, yeah, speak out. No, I mean, again, now look at here. So again, let me argue why it would happen. Okay, there will be more charges reside on this. I hope you know this one. Am I right? We studied this kind of property, isn't it? Whenever there is more curvature, more charges will reside. Whenever there is less curvature, like that. Now look at here. You can't talk about symmetry and it always be perpendicular. I mean, so you may say for a uniform surface, that's a good argument. So that you can say it is always like this. Is that okay? Equal distribution, isn't it? I'm saying you need some other argument. I'm saying you need some other argument other than the superposition of electric field. Yeah, boundary condition. That's what I'm expecting. Yeah. Inside is 0. Yeah, that is the boundary condition. Whatever you apply, that is the boundary condition. Yeah. So what did you say? So again, if any electric field exists, you can resolve that one into parallel and perpendicular to the surface. Parallel component just outside should be 0. Why? Parallel component inside is 0. Isn't it? So there may exist only surface charge for a conductor. Am I right? So again, if there is surface charge, so again, the electric field may suffer discontinuity. So, but I mean, perpendicular component of the electric field will suffer discontinuity. Parallel component is always continuous. Is that okay? So now, again, I don't have to draw this one. Am I right? Yeah. So now, let me just take one patch of area here. Electric field just below this one. Electric field parallel equal to 0. So that's why electric field parallel just outside that one. That should also be 0. Is that okay? So there may exist surface charge. It doesn't matter. Is that okay? So now look at here. Electric field perpendicular component inside equal to 0. Am I right? Outside perpendicular component of here. So that is the discontinuity. If there exists any surface charge. If there exists any surface charge, inside electric field is 0 means parallel component, perpendicular component 0. Just outside perpendicular component exists. That is the discontinuity. Okay? You can talk about that one. Continuity of the parallel component of the electric field certifies that parallel component of the electric field just outside the conductor is 0. Once you argue, again, what parallel component? Because for a surface I told there are infinitely many parallel components. Any parallel component, because electric field inside is 0. You can talk about any parallel component. Isn't it? So can you just write? Continuity of the parallel component of the electric field certifies that there will be no parallel component of the electric field. There will be no parallel component. Any problem with the video? There will be no parallel component of the electric field. What is problem? There will be no parallel component of the electric field just outside the conductor. Again, parallel component means parallel to the surface, okay, at that point. Write in bracket, since electric field inside equal to 0, or since E parallel inside equal to 0. Since E parallel inside equal to 0. This fluctuating. Can you see that? Any problem with the video? Over? Yeah, once you say all parallel components are 0, then the only thing that exists is perpendicular component. Okay? Now, there are a lot of problems here. You can just solve. You can just read out induced charges. Okay. Now I had a neutral conductor. Okay. Suppose spherical in shape. Again, if a conductor surface is uniform, then charge distribution should be uniform. Why? If charge distribution is non-uniform, there will be parallel component, isn't it? If conductor surface is uniform, look at it, if suppose more charges here, less charges here, am I right? Then there will be this kind of electric field here, isn't it? It will not allow to happen like that, okay? Whenever surface is uniform, charge distribution will be uniform. Either okay, you can take that idea. Again, read out each and every sentence here, okay? So now look at here. So I have a neutral conductor. I'm going to bring plus Q charge nearby this one, point charge. Is that okay? Then what would happen? This positive charge will attract electrons, isn't it? So then negative charges will what you call distribute here. Negative charges will appear here. So as long as as soon as those negative charges move here, so positive charges will be left out here, isn't it? I mean, usually they are ions which lost electrons. Okay, electrons moved here. Actually, electrons are free charge carriers, isn't it? Now again, this will happen, isn't it? Now look at here. Now if I ask what is the net charge on the conductor again, that's 0. Earlier it was 0. You haven't taken off any charges outside the conductor. Is that okay? You are just redistributing those charges. There were free charge carriers, there were positive ions, so you are just redistributing them. Okay? So net charge on the conductor is again 0 in this idea. Again, he's trying to say something, just read out. So now look at here. Now let me take one more idea, okay? Let me take one more idea. Now I have a conductor, okay? And I have a cavity inside a conductor. Cavity inside a conductor, okay? These are conductor region. Inside I have an empty space, okay? In that empty space, I am going to put plus Q charge, point charge plus Q. Inside that cavity, again, conductor was earlier electrically neutral. Conductor was earlier electrically neutral. There was no charges on the conductor. So what I do here is by somehow I am going to place one plus Q charge inside the cavity. Then what will happen? Negative charges will induce. Am I right? Yeah, we call this one as induced charge. Am I right? Negative charges will induce. Again, that is non-uniform. Why surface is non-uniform? Can I say like that? Induced charges should be, surface charge should be non-uniform if surface is non-uniform. If surface is uniform, surface charge should be uniform. Is that okay? So now that will be non-uniform usually. There may be more charges here, less charges here, more charges here, less charges here. Okay, whenever surface have a less curvature, then there will be less charge density. Am I right? More curvature, more charge density. Now look at here. Now it will induce negative charges here. Again, those negative charges are attracted, isn't it? From the, so inside the conductor, then obviously positive charges should be left out, isn't it? On the outside surface, isn't it? Again, now also the redistribution happened. Conductor was electrically neutral earlier. You placed one charge inside the cavity, so that charge, again, that attracted negative charge carriers inside a conductor. That's why negative charge distribution here inside cavity. So again, outside the surface, you will get positive charges. Now you can say, look at here, when you see from outside, you can't see what is happening inside actually, because here electric field is 0. Is that okay? Because here electric field is 0. Now this charge is communicating outside. This charge will tell its presence by these induced charges. This charge will communicate outside, so by its induced charges. Okay? But when you see from outside, you can't say whether there exists charge inside or not. What you can see? You can see only positive charges on the outside surface. Is that okay? Now my question is, what is the net charge inside the cavity? There is charge distribution. What is the net charge inside the cavity? What is the net charge on the outer surface? What is the net charge on the outer surface? Outer surface plus Q. Why? Apply Gauss law. electric field is 0 here, am I right? Whatever the Gaussian surface you take, isn't it? It encloses no charge, isn't it? I mean, it should enclose no charge because the left hand side is 0. You can run your Gaussian surface, though that surface is very well within the conductor region. Okay. Once you do this surface integral, obviously electric field is 0, surface integral is 0, this part is 0, that's why charge enclosed should be 0. Pure mathematical argument. Charge enclosed is 0 only when there should be as many, this net charge on the what you call inner cavity, net negative charge, that should be minus q. Is that okay? So now, again, if that is minus q, those charges are again, they moved inside, isn't it? They moved into cavity. So again, net charge should outside, that should be plus q, isn't it? Because if those negative charges are moved in, if that much electron moved into the cavity, then that many positive ions will be left over the surface, plus q. Is that okay? That is the argument. So that's why whenever you place plus q charge, so negative charges will accumulate inside the cavity, and net negative charge is minus q. Again, these negative charges are because of motion of the charge from the this one. That's why net positive charge on the outer surface, that is plus q. Okay, argue like that. Now there is one nice problem here. I think it is asked somewhere. Example number 2.10. I have a spherical conductor. I have a spherical conductor which contains cavity. I have a spherical conductor of radius r which contains cavity, and inside that cavity I am going to place a charge plus q. Okay. Now what is the electric field at a distance r? What is the electric field at this point P? Conductor was earlier electrically neutral. Conductor is spherically symmetric. Outside, when you see from outside, it's spherically symmetric. Spherical conductor, but it has a small cavity inside. Inside a cavity, again, conductor was neutral. Okay. Inside a cavity, I am going to place plus q charge. Then what is the electric field there? Now how do you start? Again like that. This plus q charge will induce negative charges. Am I right? And total negative charge should be equal to minus q. If minus q charge is there, so on the surface there should be plus q charges. Am I right? The net charge on the surface, there should be plus q. Now you have to argue that this charge distribution is uniform. Why? Because surface is uniform. Is that okay? Now you may feel like there may be more charges here, less charges here, isn't it? But that will not happen. Inside electric field is 0. There is no link. You can think like that. There is no link. So electrons moved out to the cavity, okay, cavity surface. Now positive ions are left over the outer surface, and those positive ions, they will be distributed uniformly because surface is uniform. If surface is non-uniform, again you have to go back, isn't it? If you are feeling that more charges here, suppose, then what would happen? Somewhere here you will get parallel component of the electric field, parallel to the surface. Electric field component parallel to the surface. Conductor will always avoid that. Is that okay? So that's why in the outer surface, there will be uniform distribution of positive charges. And net charge should be plus q. Am I right? Now you can. This is a uniform charge distribution problem. You can run your Gaussian surface. Am I right? And you can apply Gauss law. Your electric field at point r outside, that's equal to 1 by 4 pi epsilon naught. So q by r square r cap. Electric field outside. Now look at here. When you run your Gaussian surface, right hand side in the Gauss law, right hand side charge enclosed. Am I right? What is the charge enclosed? Plus q minus q plus q. Net charge is plus q. Is that okay? Now you can say this is communicating or this is showing its presence by this induced charge. And from outside you can see only that. Is that okay? One more argument. Yeah. What he was saying? What he was saying? Which one? Yeah, 0. He was saying 0. Why? Yeah, okay. Yeah, this was also question somewhere, okay? Maybe in TIFR they are asking some question on conductors. Sometimes, okay? Now look at here, I have one more argument. I have one arbitrary shaped conductor and I have a cavity. Okay? I have a cavity again. Now I am going to place plus Q charge nearby this one. Don't ask what would happen to this one. Okay? Let me rub it out. Is that okay? Now what would happen? Negative charges will distribute here. Am I right? Negative charges will be there and positive charges will be there. Am I right? Now my question is, what is the electric field inside? Inside the cavity. Let me take one arbitrary conductor. I have a cavity and what I am giving is, I don't know what are the charges on the surface of the conductor or not. I don't know that one. So it is an empty cavity. What is the electric field inside the empty cavity? Yeah, you are free to do anything outside. You can apply electric field, you can put charges. Why it is 0? Gauss law. But you don't have symmetry now. It's okay, isn't it? Gauss law will give the electric field only in case of symmetry. I applied Gauss law in a ulta, okay? Last time. Somewhere I applied Gauss law. Where? Yeah, there. I mean, inside I run one Gaussian surface. Electric field is 0. That's why charge enclosed should be 0. That's how I argue. Is that okay? Now you can't do the reverse one. You can't take off electric field outside the Gauss law, outside the Gaussian integral, unless that is symmetry. We are not using this one much, isn't it? Again, we applied Gauss law. That's why every time we think of Gauss law, isn't it? Now why can't you apply that one? Line integral. Now, what is the electric field inside the cavity if cavity is empty? Yeah. 0. How do you argue? Yeah. In? Yeah, again, yeah, I am placing plus Q charge here. I mean, minus charges are here. So there will be no positive charges or negative charges here. Yeah. Still, why? No, I am not getting. Yeah, I'm keeping plus Q charge outside. Okay, I have an empty cavity here, and you are putting charges outside. What are you are doing something? Now, why there is no charges here inside the cavity, isn't it? Now electrons are moving here, isn't it? Moving toward this one. Why can't positive charges somewhere distributed over there? Isn't it? Yeah. Any argument? Constant. Then again you have to use that one. Okay. Now look at here. I am going to take 2 points inside the cavity. I mean, on the surface of inner cavity, point A, point B, arbitrary. Okay. Now run your what you call line integral in any direction. in any jigsaw, so I mean, so in any manner from A to B, so then so that the line integral A to B E bar dot dl bar, that should be equal to 0, am I right? For any path, isn't it? So why that is 0 for any path? Because electric field is 0. If electric field exists, it should exist in one direction, isn't it? So then you can just argue this one, that I mean electric field is 0, that's why this line integral is 0, arbitrary line integral. You can run in any direction. You can run in any direction, so that is 0. Or you can argue in this way also. If this is not convincing, look at here, I am going to make one closed loop. Whatever happens, closed line integral of electric field is 0. Am I right? Now let me apply closed line integral of E bar dot dl bar is equal to 0. Am I right? So now in this part you have no electric field. So let me take first part, second part. So first part E bar dot dl bar is equal to 0. Sorry, yeah, that's equal to 0. So then second part should be 0. Am I right? So second part runs from one point on the surface of the cavity to other point on the other point of the cavity. Am I right? I can just argue like this. This line integral is 0. Is that okay? For arbitrary path, for very arbitrary path. So that's why electric field inside is 0. So pure mathematical argument. Is that okay? So try to argue like that. Now we call this kind of system as a Faraday cage. Okay, so now you can keep any sensitive instrument inside. So whatever happens inside, I mean, if electric field cannot penetrate, again magnetic field will not. Remember, I mean magnetic field will also not produce any effect inside. Okay, so this will be completely obstructed from outside. Yeah, you can keep any number of cavities. As long as cavity is empty, same thing will happen. Again, same argument. Pure mathematical argument. Is that okay? As long as cavity is empty, there will be no field inside the cavity. Is that okay? Yeah, that kind of problem is given here. We better to discuss later. Okay, 2.38 and 2.39. 2.38, 2.39. If you place in one of the cavity, if you leave other cavity empty, that empty cavity will have no electric field again. Same argument. Okay? Yeah. Yeah, what is that comment? Yeah? Okay. In Vishwarupa movie, at the end, so she will she will cover that bomb with microwave oven, isn't it? So that will be obstructed from the electromagnetic waves, and I mean that bomb used to be triggered by the smart mobile, isn't it? Yeah. Okay. I mean we call this one as Faraday cage. Again, just search in a Google about Faraday cage. I mean that need not be this kind of thick conductor, okay? That can be a kind of cage. Inside that cage, if you put any sensitive instrument, I mean inside that cage, I mean there will be no electric field. A kind of it will, I mean everything will be obstructed. I mean whatever happens outside, it will be obstructed. So in the inside region, okay? So again, that is used here, okay? This property is used to keep many sensitive instruments inside a cage, inside a cavity like that. Suppose if you take your aluminum sheet, okay, cover it, so cover your mobile with aluminum sheet. Aluminum sheet is a pure conductor, isn't it? So now try to call that mobile, whatever you covered. Is that okay? It will not reach. Why? Because mobile works on electromagnetic wave, am I right? Microwave. Now, electromagnetic wave contains electric field. If electric field cannot go inside, then electromagnetic wave cannot go inside. Is that okay? That's why in most of the case, in what you call inside a building or sometime, you will not be reachable to the network because of that factor. So kind of cage will happen. I mean, a kind of this kind of thing will happen. This kind of thing may happen. Okay. So you don't have to again use a thick conductor. A cage is sufficient to do this one. Okay, that we call that one as Faraday cage. Just Google it. And in that movie, at the end, so there was a bomb. They can't defuse that one. So it used to be triggered by calling the mobile inside the bomb or something. Okay. Now mobile inside the bomb will work with electromagnetic wave. Am I right? So now she covers that one with a microwave oven, so that that mobile will be not reachable, isn't it? If somebody calls from outside, it will be not reachable. It cannot be triggered. That kind of idea. Microwave oven inside, again, it will have a kind of Faraday cage, isn't it? Obviously, otherwise waves will come out. Am I right? Whatever the microwave used to heat inside, that will come out. Okay, it will have that. 2.38, 2.39, 38 and 39. Yeah, one more small concept from this chapter, capacitors. Now, tomorrow in the daytime, let me take 1 hour class and let me explain some problems in this chapter, okay? And I will keep that video, you just see that one later, okay? I want to explain some problems, only problem, not any concept, okay? I'm not sure, okay? Maybe 12 to 1. Okay, 2 to 3. 2 to 3. 2:30 to 3, so 3:30. Is that okay? 2:30 to 3:30. 1 hour, daily 1 hour, I better to explain problems, and I'm going to keep those videos, okay? No need to worry, only problems. Again, you need some techniques, isn't it? I mean, once you know the concept, you don't have to worry about that classes, okay? So that's again, because otherwise we can't finish out. Okay, yeah, even in the same schedule, if I start discussing problems, we can't finish out the whole syllabus. Is that okay? At least half an hour to 45 minutes is sufficient to solve 3 to 4 difficult problems. Is that okay? Let me discuss that one. Just take the idea later, okay? Again, so be prepared to sacrifice holidays. Yeah. Yeah. Outside, there may be like here. There's a conductor region. Electric field is 0. Okay, here and here. Now look at here. You can talk only about parallel component, isn't it? Parallel component is 0. Inside the conductor, it is 0. You can't talk about perpendicular component. It may be discontinuous. No, you have to first argue there will be no charges. There will be no surface charge. Yeah, if there is no surface charge, perpendicular component is continuous. Am I right? E perpendicular above minus E perpendicular below is equal to sigma by epsilon naught. If sigma equal to 0, yeah, that's correct. First you have to argue sigma equal to 0. So that is quite difficult. Am I right? How do you argue? I mean, if there are negative charges grabbed here, how do you argue there is no positive charge? Better to argue electric field 0 first. Okay? That's the best idea. Yeah, somebody asked that 2.50, I'll solve that one, okay, tomorrow, daytime. 2.50 and 2.52 is also needed for exam. Then we can, tomorrow I'll go to potential chapter, okay? Yeah. Sure, see tomorrow. Voice cut up. Voice surface charges are on. Yeah. Why surface charges? What's the question? Yeah, here why there will be, yeah, that's what I said. This way is a little difficult. You can't quickly argue that here surface charges are zero quickly. Okay, that's very difficult to argue. Better to first argue electric field inside is zero. If there is no electric field, then there should be no charges in the surface also. Isn't it? There should be no charges in the surface. Or you can say like this, yeah, this is the best idea. Now take Gauss law. Now take Gauss law. So take on Gaussian surface, isn't it? No charges inside the cavity, isn't it? So Gaussian surface, surface integral is zero. That's why right hand side should be zero. No charges inside, no charges should be on the surface of the cavity. Now extend your argument. Don't stop it here. Why can't there will be some negative charge, some positive charge? Again, try to argue. Okay? Yeah. No, I mean if there is negative charge, positive charge here, then positive to negative there will be electric field. Then that line integral will be non-zero. Keep on arguing. Is that okay? Play with those surface integral and volume integral, surface integral and line integral. Those two. I mean Gauss law, del dot E equal to 0, surface integral equal to Q enclosed by epsilon naught. One more, your line integral. Okay? Try to play with those. Is that okay? Mathematical.